Partitioning and Secondary Indexes. The partitioning schemes we have discussed so far rely on a key-value data model. If records are only ever accessed via their primary key, we can determine the partition from that key and use it to route read and write requests to the partition responsible for that key. The situation becomes more complicated if secondary indexes are involved. See also other indexing structures on page 85. A secondary index usually doesn't identify a record uniquely, but rather is a way of searching for occurrences of a particular value. Find all actions by user 123. Find all articles containing the word hogwash. Find all cars whose color is red, and so on. Secondary indexes are the bread and butter of relational databases, and they are common in document databases too. Many key-value stores such as HBase and Voldemort have avoided secondary indexes because of their added implementation complexity, but some such as RIAC have started adding them because they are so useful for data modeling. And finally, secondary indexes are the raison d'etre of search servers such as Solr and Elasticsearch. The problem with secondary indexes is that they don't map neatly to partitions. There are two main approaches to partitioning a database with secondary indexes: document-based partitioning and term-based partitioning. Partitioning secondary indexes by document. For example, imagine you are operating a website for selling used cars illustrated in Figure 6-4. Each listing has a unique ID call at the document ID, and you partition the database by the document ID. For example, ID 0 to 499 in partition 0, ID 500 to 999 in partition 1, etc. You want to let users search for cars, allowing them to filter by color and by make. So you need a secondary index on color and make. In a document database, these would be fields. In a relational database, they would be columns. If you have declared the index, the database can perform the indexing automatically. Roman 2, for example, whenever a red car is added to the database partition automatically adds it to the list of document ID for the index entry color :red. Figure 6-4. Partitioning secondary indexes by document. In this indexing approach, each partition is completely separate. Each partition maintains its own secondary indexes, covering only the documents in that partition. It doesn't care what data is stored in other partitions. Whenever you need to write to the database to add, remove, or update a document, you only need to deal with the partition that contains the document ID that you are writing. For that reason, a document partitioned index is also known as a local index as opposed to a global index, described in the next section. However, reading from a document partitioned index requires care. Unless you have done something special with the document ID, there is no reason why all the cars with a particular color or a particular make would be in the same partition. In Figure 6-4, red cars appear in both partition 0 and partition 1. Thus, if you want to search for red cars, you need to send the query to all partitions and combine all the results you get back. This approach to querying a partition database is sometimes known as scatter/gather, and it can make read queries on secondary indexes quite expensive. Even if you query the partitions in parallel, scatter/gather is prone to tail latency amplification. See percentiles in practice on page 16. Nevertheless, it is widely used. MongoDB, RIAC, Cassandra, Elasticsearch, Solr Cloud, and VaultDB all use document partitioned secondary indexes. Most database vendors recommend that you structure your partitioning scheme so that secondary index queries can be served from a single partition. But that is not always possible, especially when you're using multiple secondary indexes in a single query, such as filtering cars by color and by make at the same time. Figure 6-5. Partitioning secondary indexes by term. Partitioning secondary indexes by term. Rather than each partition having its own secondary index, a local index, we can construct a global index that covers data in all partitions. However, we can't just store that index on one node, since it would likely become a bottleneck and defeat the purpose of partitioning. A global index must also be partitioned, but it can be partitioned differently from the primary key index. We call this kind of index term partitioned because the term we're looking for determines the partition of the index. Here, a term would be color :red, for example. The name term comes from full text indexes, a particular kind of secondary index, where the terms are all the words that occur in a document. As before, we can partition the index by the term itself, or using a hash of the term. Partitioning by the term itself can be useful for range scans, for example on a numeric property, such as the asking price of the car, whereas partitioning on a hash of the term gives a more even distribution of load. The advantage of a global term partitioned index over a document partitioned index is that it can make reads more efficient. Rather than doing scatter/gather over all partitions, a client only needs to make a request to the partition containing the term that it wants. However, the downside of a global index is that writes are slower and more complicated, because a write to a single document may now affect multiple partitions of the index. Every term in the document might be on a different partition, on a different node. In an ideal world, the index would always be up to date, and every document written to the database would immediately be reflected in the index. However, in a term partitioned index, that would require a distributed transaction across all partitions affected by a write, which is not supported in all databases. See Chapter 7 and Chapter 9. In practice, updates to global secondary indexes are often asynchronous. That is, if you read the index shortly after a write, the change you just made may not yet be reflected in the index. For example, Amazon DynamoDB states that its global secondary indexes are updated within a fraction of a second in normal circumstances, but may experience longer propagation delays in cases of faults in the infrastructure. Other uses of global term partitioned indexes include RIAC's search feature and the Oracle Data Warehouse, which lets you choose between local and global indexing. We will return to the topic of implementing term partitioned secondary indexes in Chapter 12, Rebalancing Partitions. Over time, things change in a database. The query throughput increases, so you want to add more CPUs to handle the load. The dataset size increases, so you want to add more disks and RAM to store it. A machine fails, and other machines need to take over the failed machine's responsibilities. All of these changes call for data and requests to be moved from one node to another. The process of moving load from one node in the cluster to another is called rebalancing. No matter which partitioning scheme is used, rebalancing is usually expected to meet some minimum requirements. After rebalancing, the load data storage, read and write requests should be shared fairly between the nodes in the cluster. While rebalancing is happening, the database should continue accepting reads and writes. No more data than necessary should be moved between nodes to make rebalancing fast and to minimize the network and disk I/O load. Strategies for rebalancing. There are a few different ways of assigning partitions to nodes. Let's briefly discuss each in turn. When partitioning by the hash of a key, we said earlier Figure 6-3 that it's best to divide the possible hashes into ranges and assign each range to a partition. For example, assign key to partition 0, if 0 less or equal to hash key B0, to partition 1 if B0 less or equal to hash key B1, etc. Perhaps you wondered why we don't just use mod the % operator in many programming languages. For example, hash key mod 10 would return a number between 0 and 9. If we write the hash as a decimal number, the hash mod 10 would be the last digit. If we have 10 nodes, numbered 0 to 9, that seems like an easy way of assigning each key to a node. The problem with the mod n approach is that if the number of nodes n changes, most of the keys will need to be moved from one node to another. For example, say hash key equals 123,456. If you initially have 10 nodes, that key starts out on node 6 because 123,456 mod 10 equals 6. When you grow to 11 nodes, the key needs to move to node 3 123,456 mod 11 equals 3, and when you grow to 12 nodes, it needs to move to node 0 123,456 mod 12 equals 0. Such frequent moves make rebalancing excessively expensive. We need an approach that doesn't move data around more than necessary. Fortunately, there is a fairly simple solution. Create many more partitions than there are nodes, and assign several partitions to each node. For example, a database running on a cluster of 10 nodes may be split into 1,000 partitions from the outset so that approximately 100 partitions are assigned to each node. Now, if a node is added to the cluster, the new node can steal a few partitions from every existing node until partitions are fairly distributed once again. This process is illustrated in Figure 6-6. If a node is removed from the cluster, the same happens in reverse. Only entire partitions are moved between nodes. The number of partitions does not change, nor does the assignment of keys to partitions. The only thing that changes is the assignment of partitions to nodes. This change of assignment is not immediate. It takes some time to transfer a large amount of data over the network, so the old assignment of partitions is used for any reads and writes that happen while the transfer is in progress. Figure 6-6. Adding a new node to a database cluster with multiple partitions per node. In principle, you can even account for mismatched hardware in your cluster, By assigning more partitions to nodes that are more powerful, you can force those nodes to take a greater share of the load. This approach to rebalancing is used in RIAC, Elasticsearch, Couchbase, and Voldemort. In this configuration, the number of partitions is usually fixed when the database is first set up and not changed afterward. Although in principle it's possible to split and merge partitions, see the next section, a fixed number of partitions is operationally simpler, and so many fixed partition databases choose not to implement partition splitting. Thus, the number of partitions configured at the outset is the maximum number of nodes you can have, so you need to choose it high enough to accommodate future growth. However, each partition also has management overhead, so it's counterproductive to choose too high a number. Choosing the right number of partitions is difficult if the total size of a dataset is highly variable, for example, if it starts small but may grow much larger over time. Since each partition contains a fixed fraction of the total data, the size of each partition grows proportionally to the total amount of data in the cluster. If partitions are very large, rebalancing and recovery from node failures become expensive. But if partitions are too small, they incur too much overhead. The best performance is achieved when the size of partitions is just right, neither too big nor too small, which can be hard to achieve if the number of partitions is fixed but the dataset size varies. For databases that use key-range partitioning, see partitioning by key range on page 202. A fixed number of partitions with fixed boundaries would be very inconvenient. If you got the boundaries wrong, you could end up with all of the data in one partition and all of the other partitions empty. Reconfiguring the partition boundaries manually would be very tedious. For that reason, key-range partition databases such as HBase and RethinkDB create partitions dynamically. When a partition grows to exceed a configured size on HBase, the default is 10 GB. It is split into two partitions so that approximately half of the data ends up on each side of the split. Conversely, if lots of data is deleted and a partition shrinks below some threshold, it can be merged with an adjacent partition. This process is similar to what happens at the top level of AB tree CB trees on page 79. Each partition is assigned to one node, and each node can handle multiple partitions, like in the case of a fixed number of partitions. After a large partition has been split, one of its two halves can be transferred to another node in order to balance the load. In the case of HBase, the transfer of partition files happens through HDFS, the underlying distributed file system. An advantage of dynamic partitioning is that the number of partitions adapts to the total data volume. If there is only a small amount of data, a small number of partitions is sufficient, so overheads are small. If there is a huge amount of data, the size of each individual partition is limited to a configurable maximum. However, a caveat is that an empty database starts off with a single partition, since there is no a priori information about where to draw the partition boundaries. While the dataset is small until it hits the point at which the first partition is split, all writes have to be processed by a single node while the other nodes sit idle. To mitigate this issue, HBase and MongoDB allow an initial set of partitions to be configured on an empty database. This is called pre-splitting. In the case of key-range partitioning, pre-splitting requires that you already know what the key distribution is going to look like. Dynamic partitioning is not only suitable for key-range partition data, but can equally well be used with hash partition data. MongoDB since version 2.4 supports both key-range and hash partitioning, and it splits partitions dynamically in either case. With dynamic partitioning, the number of partitions is proportional to the size of the dataset, since the splitting and merging processes keep the size of each partition between some fixed minimum and maximum. On the other hand, with a fixed number of partitions, the size of each partition is proportional to the size of the dataset. In both of these cases, the number of partitions is independent of the number of nodes. A third option, used by Cassandra and Katama, is to make the number of partitions proportional to the number of nodes. In other words, to have a fixed number of partitions per node. In this case, the size of each partition grows proportionally to the dataset size while the number of nodes remains unchanged. But when you increase the number of nodes, the partitions become smaller again. Since a larger data volume generally requires a larger number of nodes to store, this approach also keeps the size of each partition fairly stable. When a new node joins the cluster, it randomly chooses a fixed number of existing partitions to split, and then takes ownership of one half of each of those split partitions while leaving the other half of each partition in place. The randomization can produce unfair splits, but when averaged over a larger number of partitions in Cassandra, 256 partitions per node by default. The new node ends up taking a fair share of the load from the existing nodes. Cassandra 3.0 introduced an alternative rebalancing algorithm that avoids unfair splits. Picking partition boundaries randomly requires that hash-based partitioning is used so the boundaries can be picked from the range of numbers produced by the hash function. Indeed, this approach corresponds most closely to the original definition of consistent hashing. See consistent hashing on page 204. Newer hash functions can achieve a similar effect with lower metadata overhead.